basically we will learn a little bit about what happens in normal ventilation. Okay, so normal respiration right now, when a normal person is breathing, what is the actual physiology that goes on there? There are a lot of pressure gradients that go on. That's one of the key things, or one of the main concepts in mechanical ventilation. A little bit you have to understand about what is compliance, what is resistance. Time constant, I'll just touch upon. It's a little complex, this thing. I'll just touch upon it, but I'll explain about it. And lastly, about equation of motion. I think this last part, the equation of motion, anyone is familiar with it? Any five of you or anyone online? So this is basically the crux of mechanical ventilation. And if you have to understand what happens with the ventilator, it entirely revolves around the equation of motion, which I'll come to. So all your modes and how a ventilator delivers a breath, how the tidal volume reaches the lungs, how it behaves inside the body, all this depends on your equation of motion. All right. Okay, so what is a ventilator? So a ventilator, very simple definition is it's basically a machine. It may be automatic or not, which is designed to provide a part or entire work that is required to move gas into and out of the lungs. Moving gas into and out of the lungs is nothing but respiration, simple breathing. Air goes in, air goes out, that's all. So if a machine is helping you, then that's what you call a ventilator. Otherwise, it's just normal respiration. So now, if you actually think about it, now you work with all these fancy ventilators, yeah, big fancy ventilators, NIV machines, porta vents. But the simplest form of ventilator is nothing but your manual resuscitator, AMBU, because it does provide some part of the work. It gives a tidal volume. The rate is, of course, determined by you. So this is actually the simplest form of a ventilator that we use. Okay. So now what is spontaneous respiration? Like I just now told you, spontaneous respiration is very simple. Air goes into the lungs and you expire a certain amount. But what exactly happens over here is, okay, so what happens is the main muscle of ventilation is, of inspiration is the diaphragm. I think all of you all know that. The main muscle is your diaphragm. So this muscle, if it doesn't work or it's working less, is when your accessory muscles take over or the patient will not be able to breathe and you will need a mechanical ventilator to breathe for the patient. So what happens is in inspiration, your diaphragm contracts, correct? Not just the diaphragm contracts. One thing you see is that the diaphragm contracting. So you see this animation, diaphragm is contracting. You also see the chest wall moving outward. So two things happen. The diaphragm moving down, chest wall moving out. The bucket handle, pump handle movement. If you remember your guide in physiology, this exactly. So what that is done by your intercostal muscles. So two main muscles, diaphragm and the intercostal muscles. So these are your two primary muscles of inspiration. If there is a problem with this, okay, or these muscles are not sufficient to provide adequate tidal volume, that's when you have the accessory muscles acting. You'll see your scalenii, sternomastoid, and that's something clinical that's important for you. Because if you see this acting means that something is wrong with either the lungs or these muscles. It could be a neuromuscular problem, it could be a pulmonary problem, a cardiac problem, which is why those muscles are taking over. So this contraction with the diaphragm and intercostals is what you call the work of breathing. If you actually see a very simple terminology for what is work of breathing, the work is what is done by the muscles. Okay. So I will come back to this term, the work of breathing, the muscles, the pressure generated by them. So what is happening over here right now? The diaphragm is contracting and the lungs, the chest wall is moving outward. So what is happening? The volume inside the lung is increasing. You all remember Boyle's law? Pressure is inversely proportional. Correct. Very good. At least some idea is there. That's good enough. That's what I want to know. Pressure is exactly. Pressure is inversely proportional to volume at a given temperature, at a constant temperature. Yeah. So it's as simple as that. So as the volume increases, what happens to the pressure? Pressure decreases. So interesting. These are very okay. Tell him I'm in the class. I'll call him back at 5. Okay. So what is happening is the pressure is reducing. Okay. So when the pressure reduces less than atmospheric pressure, obviously air will move into the lungs. I'll explain this better in the coming slides, but this is one way of looking at how inspiration happens. The first concept you should remember is inspiration is an active process. Muscles are contracting, whereas expiration is passive. This is a very important concept because you can somehow push lungs or force air down someone's lungs. But if it has to come out, that totally depends on the elastic recoil. It depends on compliance and resistance of the patient's lungs, which is why in a COPD patient, we always are more concerned with expiratory flow limitation. You can push in air through a ventilator, through a tube, through an IV. But if it has to come out, that is entirely passive. So if you don't correct the process, there will be some amount of air trapping. So expiration is a passive process, okay? And that requires the recoil of the lung or the lung tissue. Fine. So the contraction of muscles of inspiration is nothing but your work of breathing. So this is the first concept that I think most of you are familiar with. Now we'll go a little bit deeper. So the simpler concept is that if air has to move from one area to another, it moves along a pressure gradient, okay? And this is what the ventilators do. You have positive pressure ventilators, you have negative pressure ventilators, you have BiPAPs, those also positive pressure ventilators. So only if you create this pressure gradient will there be a flow of air from one place to another. And gas always moves from an area of high pressure to low pressure, okay? So now, if most of you all don't know what a ventilator does, just think of our lungs or our respiratory system akin to a straw and a balloon. And we will use this model of a straw connected to a balloon throughout when we discuss mechanical ventilation. So what is this concept? What is the straw? What is a balloon? The straw will be you're blowing. So this is obviously your trachea, this is your bronchi, okay, all the way up to your terminal bronchiole. So those basically not terminal, maybe your primary till the division. And the first 17 divisions where there's no gas exchange. That all, or basically it's the part of the bronchi that does not contain your smooth muscles. Okay, it does not contain cartilage. Sorry, it does not contain cartilage. All that will be your straw basically. So this is what offers a resistance to flow. Okay, all of you all are familiar with this part, right? And what will constitute the balloon? This is easy, the alveoli. This is very simple. This is basically the alveolar network. Okay. So basically, if you want to blow balloon into this, sorry, if you want to blow air into this balloon, it is via this straw, okay, which can offer a resistance to the amount of pressure or flow that you're giving in order to distend the alveolus, okay. So remember, just don't get too worried about it. Just remember the straw and the balloon. The straw is basically your trachea conducting airways, and the balloon is basically your alveolus, okay. And now if I have to distend this balloon, okay, there are a couple of pressure gradients, okay. There is a pressure gradient. So I'm now going to increase, I can increase the pressure over here so that, sorry, I can now increase the pressure over here and so that it will deliver some air over here. So there is one pressure gradient here. There is another pressure gradient between the alveolus and the chest wall, okay. Or if I add both the pressure gradient from here, the mouth opening all the way to the chest wall. Okay, so there are multiple gradients which I will discuss one by one. If it's confusing, stop me if you don't understand. Okay, the first one over here is the trans-airway pressure. Trans-airway pressure is nothing but the gradient between the airway opening and the alveolus. Okay, so this is basically from the mouth opening all the way to the balloon via the straw. Okay, so this basically is given by your airway pressure. Airway pressure is the pressure at the mouth opening or at the endotracheal tube opening if the patient is ventilated at the minus the alveolus. It's simple. Okay, so this is exactly what your ventilator is doing, isn't it? It is giving a pressure through the endotracheal tube, and that has to be given all the way to the alveolus. And the pressure in a positive pressure ventilator is obviously higher because you're giving it via the ventilator. That high pressure gradient will cause the gas flow. Okay, but this is a pressure that is required to overcome the resistance to gas flow in the airways. So if this narrows, what will happen? The pressure will increase. And if this distends, the pressure will be lesser. You all remember Poiseuille-Hagen's law formula? Any of you, at least the SRs? Poiseuille-Hagen's formula. So if I were to ask you, if I give you a patient with hypovolemic shock and I give you an option of putting central line and peripheral line, which one will you choose? JRs. Why?
The flow.
The flow?
Yeah,
This is for JRs mainly. So you guys are central line experts, so I'm asking you all this. Yeah, you're right. Peripheral line is correct. Flow is more through the peripheral line when compared to the central line. That is mainly because of the length. Okay. The shorter the length. So Poiseuille-Hagen formula is, okay, I'm just deviating slightly. It's basically a formula that tells you the flow through a tube. Okay. So the flow depends, it's directly proportional to the pressure difference, the viscosity of the fluid or the gas that's flowing, the length of the tube, and it's inversely proportional to the fourth power of the radius. Okay, so If the radius is more, then the pressure required for the drop, the pressure drop across the two ends is less. If the radius is lesser, the pressure drop or the pressure required to overcome or for the gas to flow is more. Okay. So length is there in the numerator. So if there is more length, there is more pressure required. It's directly proportional. Radius comes in the denominator. Okay. If the gas is more viscous, more requirement. So I'm deviating. So I'm just telling this for an extra thing. So basically, this is, if you want a simple term for what is trans airway pressure, if I have to inflate this balloon, the air has to flow over here. The resistance that is offering here is basically given by your trans airway pressure. Okay. So this is important for your patients when we talk about bronchospasm, COPD, so on and so forth. Next thing is transthoracic pressure. So transthoracic pressure is nothing but the gradient between the alveolus and the lung or the body surface or the chest wall. Okay, so when you're giving some amount of pressure in order to distend the lung, it's not just the lung that's distending. Also, the chest wall is also distending. Okay, so this is another important concept that you know. So that if you want the lung to expand, you're expecting the lung plus the chest wall both to expand together. And this pressure gradient is called your transthoracic pressure. Lastly, this is the most important pressure. Okay, transpulmonary pressure. So transpulmonary pressure, if I have to explain to you, so this might be a little difficult. This is why I'm going to use the board. Okay. So this transpulmonary pressure will keep on coming. So that's why I'll just take some time to explain this. So you have your alveolus, yeah, and the alveolus is surrounded by what? This is the chest wall and this is the pleura. Yes. Okay. So this transpulmonary pressure is the pressure in the alveolus minus the pressure in the pleura. What is the pressure in the pleura normally in a normally breathing patient? It's negative. Very good. And at the beginning of inspiration, this will be 0. Yes, all of you will agree. So this normally is in the range of -5. Okay. So if I have to blow a balloon, now if I give all of you all a balloon, most of you all will blow into it. That's the easiest way of doing it. You can also blow a balloon by making the exterior more negative. That's another way. So in normal breathing, what is happening is this pressure becomes more negative, and that's how air goes into the alveoli. So if I were to explain to you, so now tell me the transpulmonary pressure right now. It is 0 minus of -5. Yes. This is +5. Yeah. So this is the trans at the beginning of inspiration. What happens now when you inspire? What did I tell you? The pressure reduces, no? Diaphragm is increased, descending down, chest wall is expanding. This pressure goes from -5 to -10, around -10. So the transpulmonary pressure is now 0 minus of -10 plus 10. So because this transpulmonary pressure has become more positive, the distending pressure is increased, and that's what causes gas flow to increase. So this is the true distending pressure of the alveolus. This is important for you all to understand. Okay. Now, why this is important is, now in pneumothorax, what happens to the lungs? In pneumothorax. No, what happens? The lungs will collapse. That's all I want to say. Why does it collapse? Also, you can understand using the same concept. So you have your alveolus. Okay. Normally, the pleural pressure should be negative. But what happens in pneumothorax? There is a breach and air gets sucked in. Yes. If air gets sucked in over here, then what will happen? The pleural pressure now becomes positive, or it becomes equal to 0. It equals to the pressure. So what will happen now? 0 minus 0, the pressure is, transpulmonary pressure is 0. And whenever the transpulmonary pressure is negative or it is 0, the lung will tend to collapse. Okay. So one important concept what you should understand is the lungs are situated inside the chest wall. Natural tendency of the lungs is to always recoil inside. And natural tendency of the chest wall is always to expand outside. So if I were to remove the lungs out of the cavity, out of the chest wall, it will always collapse. But the chest wall will want to expand. At FRC, what happens is the lung maintains just the amount of recoil to stay open, while the chest wall will maintain just amount of the recoil to stay inwards. And that's what helps the normal inspiration and expiration. So this is why in pneumothorax patients, this transpulmonary pressure becomes basically 0 or it becomes If this pleural pressure becomes positive, then the transpulmonary pressure is negative, and that's why you have a collapse of the lungs. This is important for you to understand. So the distending pressure, this true distending pressure is given by this pulmonary pressure minus alveolar pressure. Okay, so nowadays in ARDS patient, we are even trying to set PEEP and stuff like that. In ARDS, what is happening? The lungs are collapsed, they're filled with inflammatory exudates. You want to keep it open so that some oxygenation will happen. So nowadays we're using this transpulmonary pressure to guide how much PEEP to set to keep the alveoli open. So these are for you people, okay, the people who will be doing DM, for you all to understand. So you will be coming for asterisk teacher, you will learn more about this. But this is the basic concept that you should take home. Alveolar pressure minus pleural pressure. In normal patients, it is 0 minus of -5, so +5. So that's why there is movement. So this is exactly what I was explaining to you all this while in a graphical form. Okay. So physiology of spontaneous respiration, what is happening over here? Okay. So normally the pleural pressure is negative, which is -5. At the end of inspiration, because of the descent of the diaphragm, this becomes more negative, -10. So what happens is basically 0 minus of -10, that's +10. The distending pressure or the transalveolar pressure, transpulmonary pressure is becoming more positive. And there is a movement of air from the mouth surface all the way into the alveolus. And vice versa happens during exhalation. At the end of exhalation, now the pressure over here is more as compared to the mouth opening. This pressure is more. So as this pressure is more, gas flow moves outwards, and this goes back from -10 to -5. So this is what happens in spontaneous respiration. In positive pressure ventilation, it's the ulta that happens. Now what is happening over here? When you're putting a patient on the ventilator, you're abolishing this intrapleural pressure being negative. The pressure is now actually positive. How this works now is, now your transpulmonary pressure is the pressure difference what you are giving at the endotracheal tube, that is at the airway pressure, mouth or upper airway pressure, basically what you are giving, that will be more positive as compared to the pressure in the alveolus. Okay. So if I were just to show you that over here you have this thing, your lungs and the alveolus, right? So the pressure over here is 0. You are basically creating now a transpulmonary pressure, a gradient. How? By giving a positive pressure over here. Okay. And the pressure is also slightly positive over here. But this pressure is more positive as compared to here. And gas will move along the gradient, and therefore it moves inwards now over here. So this funda of transpulmonary pressure is also important over here, but this pressure gradient is more important over here, your trans airway pressure gradient. Okay. So now, is it so easy that we say, I'll just give a pressure, create a pressure difference and the lung will expand? No. The lung also it's basically like a balloon. Okay. Which is easier to blow, a stiff balloon or a less stiff balloon? A less stiff balloon. A balloon filled with water or an empty balloon? An empty balloon. Balloon filled with water will be more difficult to blow. So the lungs properties that you have to know are 2. One is resistance. Next is compliance or elastance. Have you all heard of these components? We keep on telling you. So resistance is nothing but, so when I'm trying to blow air through that straw is basically nothing but tissue. It will resist. There is a natural resistance it is going to offer. Okay. That is what you call the resistance that is offered. And this is usually by your straw part of that model that I told you. Next, you have something called as a compliance or elastance. So in very simple terms, if I were to teach you what is compliance and elastance, compliance is the ease in which you can distend something. Like I gave you the example of the stiff balloon and we say a compliant balloon or a less compliant balloon. Okay. So it's the ease at which you distend something. Okay, you all would have heard the formula of compliance, no? The change in volume by change in pressure. That is the mathematical formula, which you should also understand because we'll talk a lot about that. But in very simple terms, how easy it is to distend something. Also, you should understand the lung has elastic fibers. So it's basically akin to a rubber band. Compliance is nothing but it is the inverse of elastance. Okay, it is just the ulta. So elastance means what? If I stretch something, the resistance, how much it wants to come back to its original shape. It's just the opposite of compliance. Compliance is you're trying to blow into something. Resistance means it wants to come back. Okay. So now I'll give you the example of a tennis ball and a hard cricket ball. You all have used both now to play cricket, the hard cricket ball and tennis. Which is more compliant? Which is more compliant? Yes. And the hard cricket ball, the normal cricket ball? Think. Okay, golf ball. Chalo, golf ball. Golf ball, tennis ball. Which is less elastic? The golf ball is less elastic. So that means it's more compliant. It's more elastic because it does not allow you to change the shape. It's less compliant actually as compared to the tennis ball. You understand, right? Correct. No, which one will resist the change of shape? Yes. So that's how you make it. Otherwise, if that's difficult, you just think of the stiff balloon and a less, I mean, I don't know what to say, opposite of a stiff balloon, a little more thinner balloon, okay, compared to a stiff balloon. All right. So it's basically like that. So the elastic recoil that you're talking about, it's basically the lung wants to expand or collapse back to its original shape if you're trying to blow it. Okay, so this elastance or compliance and resistance, this plays a very, very important role because you can put any ventilator and try to deliver the volume, but how much volume goes in, how much the lung actually distends, it totally depends on these two factors, compliance and elastance. And these are inherent properties of the lungs. So this is where the problem arises. This is what gives rise to all your pathophysiology. You can play around with tidal volume, you can set rate, FiO2. But what is very difficult to change, because this is inherent properties of the patient's lungs, are the resistance and elastance. So this is why you have all the, like medicines like bronchodilators, and then we prone the patients, and then we do a lot of things, diurese the patients. This is basically you're trying to play around and improve the resistance and compliance. That's what you do as clinicians, okay? So we'll just go through each of this. So resistance is nothing but it's the frictional forces that have to be overcome during breathing. So when I'm passing a certain amount of volume of gas or a pressure across that straw, there will be some resistance that are offered by the tissues, by the endotracheal tube, by the HME filter, whatever it is. Okay. So resistance is nothing but it is the formula for resistance is the trans airway pressure. Remember the trans airway pressure, mouth opening to the alveolus. So this difference is trans airway pressure divided by the flow. Okay. So this is basically derived from Ohm's law. You remember Ohm's law, voltage is equal to resistance into flow of current. V is equal to IR. Yeah? This is exactly, the R is what you want to calculate. The voltage is given by the change in pressure or the pressure difference divided by the flow, the I. Okay. So normally the resistance for a conscious patient, for patients like us who are not on the ventilator, this resistance is very less, like 0.6 to 2.4. But in an intubated patient, this is slightly higher, maybe around 3 to 5, 3 to 10 at times. Okay. So not more than 10. If it's more than 10, it's really a high resistance. So why the resistance is higher? Because here you have a tube, you have HME filters, you have suction catheters. All of this is going to contribute to the resistance of the entire airway. Okay, when the patient is on the mechanical ventilator. So common causes that you see, normally the sister will call us, no, peak pressure is high, peak pressure is high. So peak pressure high is not only meaning increased resistance. It's one of the causes, increased resistance. Your first thing is to, either give bronchodilators, suction the patient. So these are common causes. Bronchospasm, mucus plugging, kinks of the tube, patient is biting the tube, so on and so forth. Okay, so this is the clinical importance like I told you. So I think this I've already told you about trans airway pressure. Okay, how do you measure this? I will come to this later. I told you it's a pressure at the mouth opening minus this thing, alveolus. So I'll come back to this peak inspiratory. So it's actually the peak inspiratory minus plateau pressure. So I'll show this to you when we do the simulation part. Okay. So you may ask me, what is the flow? So if you actually want to see the flow is actually seen. If you put the patient in volume control, not in a pressure control mode, you can see the flow over here. This V dot is nothing but the flow. Okay, so you will get the peak airway pressure. It's on the screen. You can do a plateau pressure by giving something called as an inspiratory hold, which I'll tell you. And this part, the flow is given over here. Okay, so this is there in our Mackie ventilators. So in some machines, you basically are expected, like some of the older or other conventional ventilators, you don't have to set the tidal volume. You actually set the rate and the flow, and then the product of that gives the tidal volume. What we do over here is we set the tidal volume and the rate. So the flow is given by this. Remember what I said, no? The flow is nothing but, flow into time is equal to the tidal volume. Okay, inspiratory time is set over here. That's why your rate, and the flow is over here, and that will give you a tidal volume. Okay. So don't worry about this if it's too difficult, but if you have to calculate the resistance, this is for you all other people who have to calculate the resistance. You need the peak airway pressure, you need the plateau pressure, and you need this flow. This is where you get the flow on your Mackie ventilators. Okay, are you all familiar with it? The newer people? Priya and all, you all are familiar with it. Okay. So don't worry about it. But you'll understand the concept of what I want you to understand is that basically this is nothing but your trans airway pressure divided by the by the flow. That's what gives your resistance. And resistance is given by your trans airway pressure. And why this is important is because if there's any change in the trans airway pressure, there'll be a change in the ventilator waveform, which I hope I should be able to demonstrate to you on simulation. Compliance, like I said, it's the inverse of elastance, the ease at which you can distend something. Okay. So if something is more stiff, you will need more pressure to give the same amount of volume. Yeah, it makes sense, right? So basically, change in volume by change in pressure is the formula. Change in volume by change in pressure. So people who are attending cardiovascular coursework also, we're talking about compliance here also. I think even Matthew talked about this. So it's nothing but if basically the compliance is decreased, that means the balloon becomes more stiff, you need to generate more pressure to keep the tidal volume constant. It's as simple as that. Okay, so this is important, especially when you are talking about pressure control modes. So in pressure control modes, you will set this delta P. As an operator, you're setting this basically in order to generate a tidal volume. Okay, so if I was keeping a pressure difference of 10 and I was getting a tidal volume of 500, if suddenly for some reason the compliance of the lungs reduces, what is going to happen? For the same 10 pressure support, what's going to happen to my tidal volume? It's going to reduce because this and this is, yeah. And then your machine will start alarming that the tidal volume is less. This is more important for your pressure control modes because in pressure control modes, you are setting this. Okay, this is not so much important for your volume control modes. So now, compliance is not just offered by the lungs. Even the chest wall is an elastic structure. Okay, so even if your lungs are normal, but there is a problem with your chest wall, there also this formula applies. Okay, so this delta P can be a problem either in the lungs or it can be a problem with the chest wall. One common example is gross ascites or massive pleural effusion. Okay, so that what will happen, or obesity or kyphoscoliosis. All of these shade will affect the compliance of your chest wall. The lungs might be normal, the parenchyma will be normal, but these patients will also require a higher pressure to inflate the lungs to a set tidal volume. Okay, is this concept okay? Compliance. Okay, so normal compliance usually ranges between 70 to 150 or so. Okay, if you want an easy way of remembering, it's around 60 to 100. Okay, so the unit is very simple. Unit is what's on the denominator? Volume. So it is either ml or it is liter divided by centimeter of water because that's the unit of pressure. So that's why you have the ml by centimeter of water because it's basically change in volume by change in pressure. Elastance, on the other hand, is nothing but change in pressure. Like it's just the inverse, exactly the inverse. Okay. Don't worry about elastance. At least if you understand compliance, this should be good enough. Okay. So these are the factors that alter your lung compliance. Okay. Lung compliance, basically in pneumonia, what happens? The alveoli is filled with some inflammatory fluid. Same thing in ARDS. In atelectasis, the lungs are collapsed. So if I have to make you easily understand this concept of atelectasis, is it easy to open a collapsed balloon or a partially open balloon? It's always easier to blow into that. So if it's fully collapsed, that's where atelectasis, yeah. So that will also reduce your compliance. Fibrosis, of course. Fibrosis, there'll be a destruction of your yeah, there'll be a destruction of all your elastic fibers. It's stiff. It's difficult to inflate. Compliance is increased, on the other hand, in emphysema. Okay, and conditions that affect the chest wall compliance. This also I've told you: pleural effusions, gross ascites pushing the diaphragm up, kyphoscoliosis, obesity also, burns contractures around the chest walls, so on and so forth. Okay, so now this might be too much for you guys, but the other guys should know this. So there are two types of compliance we measure. One is the dynamic compliance and the static compliance. Okay, so dynamic compliance. Sorry, first I'll start with static compliance. So now, how do we measure the compliance? Have you all seen us look for plateau pressures? You guys? Yes or no? Some of you all have. Okay. So basically, when I was talking about the alveolar pressure, no, P alveolar minus pleural pressures. So how do you measure what is the pressure at a given point of time in the alveolus? That's important for you, no? So all your pressures are either airway pressure minus alveolar, alveolar minus body surface. So you need a surrogate for this alveolar pressure. So what we do is when the patient is on the ventilator, we create a no flow state. Okay. So this is what I mean by that. So this is basically your pressure waveform. This is pressure against time. Pressure time scalar is what we call it. Okay. So what you see over here is now when I'm starting inspiration, so the pressure is going up. And then what I will do is I will press this inspiratory hold button. What I'm doing by this inspiratory hold button is I'm telling the ventilator stop all flow. Don't give any more flow to the alveolus. So what will happen? The pressure will immediately drop and become static, or it starts to get static. Okay. So this pressure actually should tell you, this plateau pressure should tell you what exactly is going on in the alveolus, because at that point of time, there is no gas flow. Correct. And these sensors are all present at the level of the, the inspiratory or the expiratory limb towards the eyepiece, outside of this thing. So if there's no flow, what basically at that time the pressure sensor will be picked up is basically what is reflective of the alveoli in both this thing, in both the sides of the lungs. Okay. So that is nothing but your plateau pressure. So this plateau pressure gives a great information about the static compliance of the lungs. Okay. So if the patient has an increase in resistance or a decrease in compliance, increase in resistance or decrease in compliance. So basically, if there's a problem in the straw and the balloon, in both these conditions, the peak pressures will increase because the pressure required to inflate the lung over here, irrespective of the problem here or here, is going to be more. Okay. So peak pressures can tell you that there is a problem in resistance or a change in the compliance. But if I need to know that the problem is only here at the level of the alveolus or the chest wall, a compliance the plateau pressure is what is going to give you the information. So even if the plateau pressure is also increased along with the peak pressure, that will tell you that, so that means it will tell you that there is something going wrong. It's either this or it's this, and that's what you have to figure out from doing all your tests, ultrasounds, X-rays, so on and so forth. So this is why this concept of static compliance is important. Okay. So compliance is what? Compliance is change in volume by change in pressure. So your static static compliance is nothing but tidal volume. Why is it not delta V? Because it's basically 0 minus the tidal volume, or tidal volume minus 0. To begin with, this was 0, right? You're giving 500. So that difference is, say the tidal volume is 500. 500 divided by your plateau pressure minus P. So how do you get PEEP is basically, did I tell you about the concept of PEEP yet? No. I'll come back to this. PEEP is nothing but, you would have heard of this concept, PEEP, CPAP. PEEP and CPAP is nothing but it's the same. PEEP is basically a positive pressure that is present in the alveolus at the end of expiration. Correct? So the lungs never fully close, isn't it? Our lungs are always partly, even if you try to forcefully exhale, there's still some amount of 150 ml of residual volume that is there. The lungs, this is because of a surfactant, okay? So the positive pressure that is there at the end of expiration is nothing but your PEEP. So PEEP is the term you use for a mechanically ventilated patient, and CPAP is the term you use for a spontaneously breathing patient. But the idea is the same. It's a positive pressure, and it's there throughout inspiration as well as expiration. In a patient who's on the ventilator, it's more important towards expiration because you expect at expiration everything would have gone out, but no, there's still some amount of positive pressure. So this positive pressure, normally we set 5. You see that, right? Normally all of us will set 5 and we keep it. We very rarely set 0 unless there's a certain like COPD conditions. This 5 is what you call as a physiological PEEP. This physiological PEEP is generated at the level of the larynx because your vocal cords are partly closed, and that itself maintains some amount of PEEP. That is called your physiological PEEP. Okay, but if that is not sufficient, and I want to keep the lungs open throughout, or I want to keep it open because of some pathological condition, then I can titrate my PEEP. I can increase the PEEP to keep my lung open at the end of expiration. Okay, so I'm not going to talk about that because it might get a little bit too much physiology. But I hope you understood the whole concept of PEEP and CPAP. So what you're doing in NIV, what you're doing in BiPAP, you're doing the same thing. You're giving a positive pressure throughout, isn't it? You're setting IPAP, you're setting EPAP. You can keep an EPAP of 0. You can just keep a pressure support of 10. That's called CPAP, a continuous airway pressure. It's basically a pressure that is required to keep your alveolus open. That's all. It maintains it open so that there's a good, adequate tidal gas exchange that happens throughout inspiration as well as expiration. Okay, so that's the whole idea. So this helps in your patients with COPD. It helps in your patients with cardiogenic pulmonary edema. It just is to recruit the alveoli, prevent it from collapsing. That's the whole idea, so that they can participate in gas exchange. It's also helpful in your atelectasis patients. Okay, so that's what PEEP is. So compliance is nothing but the tidal volume divided by static compliance by plateau minus PEEP. Okay, so this is something that we commonly measure, especially in a patient who's on a mechanical ventilator. So why we do this is because this gives us an idea of the alveolar pressure. What's the pressure at that point of time? If this compliance is affected, then it is our job to fix the problem, because otherwise it will be difficult to distend that alveolus. It will be difficult to deliver tidal volume to that. If I do try to deliver the tidal volume, it can cause barotrauma. It can cause ventilator-associated lung injury if I don't correct this compliance. And this idea of static, why is it called static, is because you're creating a no-flow state. So if you're having a patient who's breathing and you're trying to press inspiratory hold, then you're going to get an erroneous value. It will not correctly reflect the alveolar pressure that you want to measure. Did that make sense to you? Like you're trying to create a no-flow state because you want to know exactly what is the pressure in the alveolus. But if the patient is trying to breathe against that, then this pressure difference may not reflect it. Okay? No, Priya, didn't make sense. Understood? Okay. So static compliance, why is it called static compliance? So basically, why you're measuring the static compliance, you're taking the plateau pressure, correct? So if you have to measure so this question was asked to one of our DM residents, how did you measure the plateau pressure? Ideally, you should put them in a volume control with an inspiratory hold, with the patient not generating an inspiratory effort. Because what you're trying to do, you are basically trying to pick up the pressure in the alveolus in a no-flow state. You're trying to basically bring down this flow. You're trying to make this a no-flow state so that you can identify what the plateau pressure or the pressure in the alveolus is, basically the true pressure. Okay, but if the patient is breathing over here at this point of time, you're seeing fluctuations, then this measurement might not be correct. You can measure it, it will give you a value, but it may not reflect exactly the P alveolar or the static compliance. Okay, does that make sense to you? So it should be in a no-flow state, ideally, if you want to do a plateau pressure. Okay. So now coming to the concept of time constant. It's okay if you guys don't understand this, but for you guys, at least you all should understand what time constant is. This will be dealt in detail in asterisk also. So now we talked about compliance, we talked about resistance, right? So remember I told you all, I'm not going to talk this, like I have a full 30-minute talk on this in asterisk. I'm just doing 2 slides over here. Basically, you want the lung to expand. So the lung expansion and lung emptying, filling and emptying. Okay. So like we already discussed that this is the recoil part is a passive process. So now how much time it takes for the lung to fill? Now, if my lung is very compliant, it will fill very fast. If my lung is less compliant, it might take longer to fill. Yes? Or think of the straw. The straw. If I take a thinner straw, I'll take more time, more pressure to distend that balloon. If my straw is big, lesser time. Okay? So time constant, a very simple way, is basically your time taken by the lung to fill during inhalation and empty, if the same gas flow rate is mentioned and is maintained. And this is given by the product of resistance and compliance. This is a tough concept for you guys. I don't even want you all to break your head too much about it, but I'm trying to make it simple. Just think of a stiff balloon or a stiff straw. If it's stiff balloon, compliance is less or more? Less compliant. Okay, and if the straw is thinner, resistance is more. So if the resistance is more, what happens? See, the formula is R into C. So I've given you one example over here. So if the R is narrowed, if it's narrowed, the R is increased. Yes, increased R means my time constant, which is given by this Greek alphabet called tau, is more. So I'll need more time to distend this and more time required to empty. That is more important for me when I'm treating my patients with increased resistance. Very common example for this is your asthma patients, your COPD patients. Yes or no? Okay. So if you don't give enough time for expiration for them, you will give rise to gas trapping. This is what happens. The air does not have enough time to get out. So that's what causes gas trapping, dynamic hyperinflation, autopeep. You would have heard all these terms previously. So this is the whole idea. You have to give adequate time for exhalation in these patients. Okay. So normally, if you see, this is how it takes. The time constant, normal time constant, like at the end of one time constant, product of R and to C, 63% of the lungs will either fill or empty. At the end of two time constants, 86% of the lungs will either fill or empty. At the end of three time constants, 95%. So this is good enough, right? You should give at least 3 time constants, okay, for adequate exhalation, for 95% of the gas to move out, okay, which means that you need to optimize the resistance or the compliance, whichever is causing the problem. Because if the resistance is increased or the compliance is increased, then my time constant will increase. And if I don't fix the problem in what is causing the increased resistance or compliance, there'll be more time required for it to inflate and more time for it to deflate. And if I don't give adequate time, it will give rise to gas trapping. And that gas trapping has its own physiological complications or consequences. Okay, so it's okay if you don't understand time constant. I didn't even intend to tell you about this because you all are still awake, I'm telling you all. But this is a concept that you guys need to understand. I hope you all understood this concept. Anyway, this I cannot tell you because this is a separate class by itself. I'm just trying to explain to you what happens when you're inflating or deflating, how important R and C is, this resistance and compliance is. Because if the resistance is more time required to deflate. Okay, so even if you don't understand this, leave it, don't bother. But until here, you all understood the pressure gradients, the concepts of compliance, resistance, something has got into your head. Okay, so there are 3 types of ventilators actually, if you see what are these? Positive pressure ventilation. What it means by positive, we are all negative pressure ventilators, yes? Our intrapleural pressure is negative, we make it more negative, and that's how gas. Have you heard of any machines that can do that? That can generate an intrapleural pressure, making it more negative? Yes, beautiful. This is the iron lung. So this is how an iron lung looks. So this is basically, you can see the man's head sticking out. So this man is still alive on an iron lung. So that's why I put this photo till this date. He's a polio survivor. And you can see him happily drinking, eating and stuff like that. And very happy in that. So this is basically, you have different variety. Oh, sorry. Okay. But you understand, right? You can see his head sticking out and the rest of the body is here. So what this is doing is basically, it is making the pressure at the body surface more negative. Yes. So it's making your transthoracic pressure more negative. What is it doing by that? It's making the intrapleural pressure more negative. So the same formula, -5 will become -10. So the transpulmonary pressure will become positive and then the alveolus distend. So this is one way of ventilating your patients, negative pressure. What we are doing is positive pressure. I'm giving a positive pressure at the mouth opening. The pressure here is 0. That's creating a pressure gradient and air is moving in. This is what your positive pressure ventilation does. Okay, so 2 types of ventilation. There's another type called high frequency oscillatory ventilation. This has a different funda altogether. Here you're giving less than tidal volume breaths at a very high rate. Okay, so this basically generates breath or generates gas exchange through convection, through penduloft movement. It's okay if you don't know about this. This is another thing. This is more commonly used in pediatrics. We don't use it now. There's no trial also which supports the use of HFOV right now. We commonly use positive pressure ventilations. Negative pressure ventilation used to be used. Actually, this is the birth of mechanical ventilation. Mechanical ventilation never started with positive pressure. It started with negative pressure ventilators and its use boomed during the COVID period. Sorry, not COVID, the polio period, the polio epidemic. And that's how the whole concept of the iron lung and all that is, which I showed you over here. Okay, so now coming to the last and final concept, the most important concept of, so I told you so many things, no, work to breathe, pressure generated by the muscles, and that pressure has to be overcome by the straw in order to distend the balloon. So if I had to give you a very simple terminology or a very simple equation to explain this, it is the equation of motion. Okay, so equation of motion, all of you all remember Newton's third law? Every action? Exactly. Okay, so the action what you're giving over here is a pressure. Okay, what you're trying to give a pressure to distend your alveolus, your lungs, whatever. But it has to overcome the resistance, it has to overcome the compliance. So that is the opposing forces that is generated by your lung. Okay, you're trying to give, someone's trying to call it. You're trying to give a pressure to open the lung, but the opposing forces are what is generated by the lung in terms of compliance and the resistance. Okay. So if you see on the left hand side, you have pressure. Yeah. Pressure, P vent is if the patient is on the ventilator. P muscles is generated by the patient, that is by the diaphragm, by the intercostal muscles. Now, if my patient is spontaneously breathing, this automatically becomes 0. So it's only the P muscles. If your patient is it's paralyzed and the ventilator is doing all the work, this becomes 0. And this is only P vent. If the patient is on an assist control work mode of breathing, where both are happening, then both will be in play. Okay. But how much pressure is required to generate? It depends on the, remember your straw and your balloon, your trans-airway pressure and transthoracic pressure. Okay. So this resistance into flow plus compliance. Compliance is 1 by elastance, or elastance is 1 by elastance into volume. Okay. So there are two factors that will tell you how much pressure is required to distend your balloon at the end of the day. Okay. So this is your equation of motion. Okay. The pressure required to overcome the straw and the pressure required to overcome the recoil forces of this balloon. Okay. So it's given by resistance into flow plus elastance or compliance, 1 by compliance into volume. Okay. So what is the importance of all this? I'll tell you now. Okay. This basically is called your resistive load. Okay. So if there is an increase in the resistance, more pressure has to be generated by the muscles. It's as simple as that. If you put the ventilator on, then of course the ventilator will assist the patient. So in simple terms, what it means is that if there's a problem with my resistance and if there's a problem with my compliance, if I have to generate an adequate volume or flow, one of these two things has to work well. If the muscles are not doing the work, then it has to be assisted by a ventilator. That's all it means. Okay, that's how your equation of motion is. So if you see on this equation, you have, okay, I think I'll better draw it. You have pressure on one side equals to volume and flow on the other side. Yes, flow and volume on the other side. All right. So as a ventilator, it has to overcome one thing. This is the resistive load that's offered by the straw and the elastic load. The elastic load is basically by your pressure by the balloon. Yeah. So now, why this is important is because a ventilator can control only one of these things. Can it control the compliance and the resistance? Those are inherent to your lung. Yes. So if I have to distend the lung through that straw by pushing air through that straw, your trachea, the ventilator can either control the pressure or it can control the flow or volume. Flow and volume are interrelated. Speed is distance into time. The volume is nothing but flow into time. Okay, so these are linked. So that's why when you talk about ventilator, we talk of two common modes. One is your pressure control mode, volume control mode. So the ventilator can take control of only one of this. It cannot be a pressure controller and a volume controller, both. It's never like that. Okay, so the variable that the ventilator controls is set by you. And that control variable is what the primary variable is. It's basically like only three variables. It's basically pressure, flow, volume. But remember, flow and volume are linked together. You can either set the flow, and depending on the inspiratory time, volume will be given. Or you can set the volume, and depending on the respiratory rate, that flow will keep moving up and down. Okay? So either the pressure or the flow or bar volume can be controlled by you as a controller. Okay? So this is how you get the concept of pressure control mode and volume control mode. Okay? This much is easy. So that is why the equation of motion is important to understand that. So equation of motion, remember, it's the pressure required to overcome this resistive load as well as the elastic load. Resistive load is nothing but resistance into flow given by a straw, the balloon, the elastic tissues over here, as well as the chest wall. Okay, that also contributes elastance into volume. Okay, so if my resistance is more or compliance is less, this pressure required to provide volume or to provide flow has to simultaneously increase. That's how the equation works. Okay. So that's how Chatburn has given these multiple kinds of modes. Okay, these are the modes of ventilation. Don't break your head. For JR level, pressure control, volume control. Even for SR level, it's enough. If you know this, this is good enough. Because the ventilator can be only one of the two, either a pressure controller or a volume controller. Okay. So now, I showed you this picture earlier, right? So tell me, is this a pressure control mode or a volume control mode? JRs. Why is it a pressure control mode? Okay. SRs. Is it a pressure control mode or a volume control mode? Why is it volume controlled? Where waveform? What happened to the waveform? Very okay. So what this simply means is, if you understood the equation right, is that if you are controlling the pressure, what is going to change? Only the flow of volume. If you are controlling the volume, what is going to change? The pressure. Is your pressure changing or it's remaining the same over time? It's changing. Now it's doing a dance. If it was remaining same, it would have been same. Yeah, but you're seeing it change. It is slightly increasing. This is the peak that you've set. The peak, that's why it starts here. This is the pressure on the y-axis against time. So the pressure is increasing. This is during inspiration. This is a plateau pressure you have set because you put an inspiratory hold. Then it's coming down in expiration and is reaching the peak at the end of expiration. So if this was a pressure controlled, you would have seen it just static. Okay. So shall I show you the ventilator so that you'll understand? I'll show you the simulation. Just tell me if you all will be able to see this on the screen. Okay. Is it seen for you guys? Is my screen visible? Okay, I'll share my screen. Just 1 second. Did you have any doubts still here, by the way? Yeah. Sorry, tell me. Any doubts till this point of time? Can all of you see the screen now?
Yes.
Sorry. Yeah. Cool. So if you see over here, what you're seeing now is basically three things you see on the ventilator. Two things rather, scalars and loops. Okay. These are called scalars and these are called loops. Okay. So these are scalars, these are loops. Scalar is nothing but measurement of a variable. What are the variables I told you in the equation of motion? Pressure, flow, volume. Okay, so first one is, you can see centimeters of water. So that's obviously pressure. So this is pressure versus time. This is flow versus time. And this is volume versus time, which is not very clear over here, unfortunately. But in a, what mode is this? Volume control mode. So what did I tell you about volume control mode? Pressure changes, but volume sets remains same. So what have you set? 400. So it will deliver 400. Okay, here it's not delivering because of your alarms. Okay, so if I change my alarms, am I able to change it down to? No, I'm not able to change it. See if this works. Is there a change? Come on, come on. Okay, for some reason this is not working. That's all right. Actually, I can change the resistance and compliance over here. So if I change the resistance and compliance, you're going to be able to see changes in this. Because what did I tell you? That in the equation of motion, you can play with either pressure or volume. So this is volume control. So the change in what will change, the pressure will keep changing. But the pressure change depends on the two inherent properties, that is the resistance and the compliance. So you will actually see a change in this waveform. Okay. So since I'm not able to demonstrate it for some weird reason, let's try one last time. If it doesn't work then. It was working in pressure control. It's working in pressure control. Unfortunately, it's not. You've made a change in the wall flow, no? It's changing here, but it's not changing here. I don't know why. Okay. Just try volume control again and see if it works. If it doesn't, then I'll draw and show you. Okay. Fine. Yeah, I think it's better now. Fine. So what is going to change now is your volume control. So in volume control, if you see this, there's a small like rise and then it reaches this peak. So this pressure, the maximum pressure that you achieve in a volume control for every breath is what you call the peak pressure. So I told you peak pressure can happen if there is a change in the resistance as well as a change in the compliance. But if you want to see only a change in the compliance, there has to be a change in P plateau. So there has to be an increase in the plateau pressure also. Okay. Now I'll just make some changes. See if you're able to appreciate it. Okay. Look at the pressure waveform. Venetian? Really not changing here. It's a pain. Now you can see this. You can see that has gone up. You saw that as compared to this. So if I were to draw it and show it to you, I were to draw it and show it to you. This is your pressure control. Pressure times scalar. Pressure times. So what will happen is, this is a normal pressure time waveform over here. Okay. So this part will increase. This is the part, this small slope, that is the amount of pressure required to overcome the pressure by the straw. That is your resistive load. This part is your resistive load, and this slope is given by your elastic load, that is by your balloon. So in case I increased the pressure or the cup resistance, let me see if it works now. Look at this thing over there. I've increased the resistance. Now see, can you make out a change now? You can make out? It has gone up. Now you'll not be able to. Okay, let me reduce the resistance and see. Okay, now see if there's a change again. Can you see? Yes. All I've done is played around with the resistance. So the resistance increases, this will increase. So automatically your P peak is also going to increase as compared to here. Okay, fair enough. So this part of the pressure waveform, the initial upslope, that part where it just takes off, if you all go back after this and put a page, see a patient of volume control, then only you will remember it better. Okay, so this is by your compliance. Now, sorry, by your resistance. Now, I'll make another change now. First, I'll reduce the resistance so that you remove all the resistance component. Now, you concentrate only on the slope. Okay. Okay. So this is actually a normal compliance. So this is how the slope will be. As my compliance reduces, this slope will keep going more and more up. Okay, so I'm going to reduce the compliance now. Can you see the change in the slope? Understood? So what happens is, we'll draw this. So if there's a change in resistance, my P peak will increase. If there's a change in compliance with no change in resistance, my slope goes up. Here also my P peak increases. So peak airway pressure will increase if there's a change in resistance or a change in compliance, where the slope becomes more or more obtuse. Okay. And if I need to know what is the problem causing, is it a resistance problem or a compliance problem, the method that I can use is pressing the inspiratory hold. If I keep an inspiratory hold, then you get your plateau pressure. Normally, the plateau pressure, we try to aim it less than 30 centimeters of water. So you can never keep a fixed value. You have to know the baseline value for your patient. Okay, say his plateau pressure was 10 and now it's become 80, or now it's become 20, or now it's become 30. So that itself tells you that there has been a decrease in the compliance. That's why your plateau pressure. Remember the formula, right? Delta V by delta P by delta P. Okay. So the tidal volume obviously is remaining constant. It's volume control. You're not touching the tidal volume. Only the delta P is going to change because your plateau pressure has now gone. Okay. So that's why your compliance is going to come down. So you all understood that. No, so PP can be because of an increase in resistance or a decrease in compliance, but the plateau pressure is what's going to help you if it's a compliance problem. Fair enough? Okay, so if there is a tube block, also there is going to be a peak pressure increase. But if there is a tube block along of the tube is normal, but you see there's suddenly a pneumothorax. If there's a pneumothorax, what's going to happen? The compliance lung is collapsed, so obviously the compliance is going to reduce. So both the peak pressure will also be high, plateau pressure is also going to be high. Okay. So you're understood, no? In volume control, all you can do is set the volume.
At that point, when you wings critical and then you check. So differentiate.
Differentiate. That's how you will get the plateau measures. Okay. So that is one concept. Now I will switch to this. You understood the volume control, right? Now remember your equation of motion. What happens in pressure control mode? Pressure is the control variable. Yes. So now see this over here. Now I need you to appreciate the pressure waveform. Now can you see the pressure waveform? It's no longer that triangle. Now it is. Oh, sorry. Yeah, it's a plateau here. Can you see now? Pressure. What is changing?
Volume.
Volume will change. Volume and flow is obviously interlinked. What you're seeing now is flow. Can you see the flow? Yeah, okay, wait, I didn't show you the flow in the previous mode, right? See volume control. See in volume control, how is the flow? Constant. What about here? Is it constant here? Very good. So expiration is a passive process, which is why in inspiration it's constant, but once it cycles into expiration, the lung emptying totally depends. It's a recoil process, which is passive. Okay. So this part depends again on your resistance and compliance. I'm not explaining the formulae, which are very complicated. Don't worry. But at least I'm glad you all understood that concept, that this part is changing because it's an expiration. But the flow is constant. Because the flow is constant, flow into time gives you volume. The volume will remain constant, which is 400, whatever you've set. You've set 400 or 390, 400, it will deliver that much. Understood? So now, if you compare the flow volume loops, 1 second. This is shading a lot. If you see PRC, sorry, pressure control. Okay, pressure control, now see immediately the change. The pressure is now the constant or the controller, and what is changing now is flow. And flow is going to change both in inspiration and expiration. Expiration because it's a passive process, but here you see a decelerating flow, which is very typical of your pressure control mode. So what is basically happening is in pressure control mode, you're setting a delta P. You have to set the trans airway pressure or transpulmonary pressure, right? So you have to create a positive pressure at the mouth opening. It is assumed to be 0. Now, if you've kept PEEP, then it will be PEEP value. If you've kept a PEEP of 5, because that's the pressure that you wanted to keep in the alveoli at the end of expiration, PEEP, that's what it means. So if you kept 5, so it will be, say you put 20 minus 5. So this pressure control is basically 25. So you're basically creating 25 minus 10. So that is the pressure gradient that you are setting. Okay, and tidal volume will depend on what? On the compliance and the resistance of the lung. Okay, so now see, I'm going to change the compliance and resistance, and you tell me what is happening. Okay, I've made some change. Now it was delivering 350. Okay, how much is it delivering now? This is 350. It was 350 earlier. Now it is delivering 299. So why this has happened is because I have altered the resistance of the lung. Okay. So now what I'll do is I'm going to decrease the compliance, and now you see what happens. 1 second. Make it resistance normal. Now, see now how much is it delivering? 483. This is the normal lung. Now the patient is absolutely normal. Now what I'm going to do is I'm going to reduce the compliance. Just wait. What has happened? Tidal volume has decreased. Yes. So you all understood? So basically the tidal volume. Now this is a pressure control mode. The volume or the flow can vary. And how it's going to change, it totally depends on the compliance and the resistance of the lung. So if my compliance of the lung is less, that means stiff balloon. Remember that, stiff balloon. So even if I keep the same amount of pressure, it is because it's stiff, it's going to be difficult to distend. So it's going to generate a lesser tidal volume. So a typical example is if this patient suddenly has developed a pneumothorax, if the patient suddenly has a pulmonary edema, if this patient suddenly develops one side collapse with mucus plug. So all of these causes will cause this sudden drop in this thing. Do we use pressure control in the ICU? Yes, only one person saying yes. Do we use? Have any of you seen?
Use for BPF patient.
We use for BPF patient. Okay, so I'm going to give you a trick question now. All of you all use this mode, yeah? Yes or no? Okay, this is actually a Dabba ventilator when it comes to PRVC. This is not a great simulation, but okay, I hope I should be able to give you the gist of it. Come on. Okay, this is not a great example. So, okay, fine. So people who are using PRVC day in and day out, sorry, JS, this is not simulating. It's not a good simulator for PRVC. People who are using PRVC day in and day out, is it a pressure control or is it a volume controller? It's a? No. It's a pressure controlled breath. So unfortunately, it's not showing over here. But actually, if you go back now, go and see any patient on PRVC right now, just go and see the ventilators. You will see a constant pressure. It's a dual mode. Okay, so what we are using is dual mode. So did you see in pressure control when I reduced the compliance, how the tidal volume went all the way from 400 to 100? Do you want that to happen to your patient? You want to give a stable minute ventilation, yeah? So that's one of the limitations, that if there are large changes in the compliance, you will not be able to give a stable minute ventilation with pressure control. So the PRVC gives you the best of both worlds. It gives you the stability of pressure control. So pressure control is one of the modes associated with better oxygenation. It maintains a mean airway pressure. Better oxygenation is achieved with pressure control. But only problem is the tidal volumes are not going to be static. I mean, they keep changing the minute ventilation. So that's where we can set a volume also. Okay. So it basically gives a guaranteed tidal volume at the least amount of pressure or transpulmonary pressure. That's the advantage. That's why we use pressure regulated volume control, but it is a pressure controller. So at the end of this class, all of you will go and see a patient on PRVC. You will see the same findings or the same kind of graphs as you see with the pressure control, which is basically a decelerating flow. It's a decelerating flow and you will see a constant pressure. Okay, but in PRVC, you can give the machine the choice of how much tidal volume you want to give. And it will do this PC minus P business. It will do it. It will first give, if you actually, for an experiment, try a test lung, take a test lung, put a patient from volume control to pressure control mode, or PRVC mode, sorry, PRVC mode. What it will first give on PRVC is a volume control breath, and then it will switch to a PRVC mode. That's a pressure control mode. Why it does that is first it will give you a volume control breath. It will measure the compliance and resistance from the peak pressures. It will measure it. And then for the least amount of pressure that is required to achieve the tidal volume, it will set it. So it will only give you, it will only calculate this pressure control minus P. You don't have to set it. Okay, you do set it in the alarm limits, but that's a little bit complicated. I won't tell you that. But remember, that's how it sets it. Okay, so pressure control PRVC, what you'll use is a pressure control. I think this is enough for today, right? At least I gave you all the concepts of pressure control, volume control, equation of motion, this thing. PS CPAP is another topic by itself. CPAP, that's spontaneous breathing. Today I only talked about controlled breathing. So I hope it made a little bit of sense. Too much